Okay.
All
Well,
right.
I'm sorry.
All right, let me give you the introduction. So today we are happy to have John Nahay here, and he'll talk about factoring all the terms of a differential resolvent.
Well, I'd like to thank the organizers for having me, and I'd like to thank the viewers for taking your time to watch this. Dedicate this talk to a friend, mathematician Scott Forrest, and to my dissertation advisor, Dr. Richard Cohn. So first, I'll just talk about the purpose of differential resolvents. So the original historical motivation for differential resolvents was to find roots of a polynomial. We already have formula for all roots, such as given by Sturmfels. But resolvents were a way to compute arbitrary powers of roots. Later, they became a way of linearizing the polynomial by finding various linear combinations of derivatives among derivatives of arbitrary powers of the roots. More interesting differential relations among the function z were discovered, where z is algebraic over a field generated by a finite set of intermediate variables, e1 through en of x, which themselves may be algebraic, transcendental, or even differentially transcendental over rational functions of x. This led to the hope of possibly finding ways of solving systems of nonlinear differential equations by towers of extensions of solutions of linear differential equations. So in this talk, let z be the ring of integers. Script n is the set of positive integers. Script n sub 0 is the set of non-negative integers. Script q is the field of rational numbers. Script c is the field of complex numbers. When n is a positive integer, square bracket n is the integers 1 through n, and square bracket n sub 0 is the integers 0 through n. And throughout the talk, capital N will always represent the degree of this the polynomial of that I'm taking the resolvent of. We call a univariate polynomial P of t of degree n a differential polynomial if its coefficients e sub k, or the kth elementary symmetric function of the roots of p, possess a distinguished derivation d, a total derivation. We think of the root z1 through zn and the coefficients e1 through en as being functions of a variable x such that dx is 1, but x doesn't have to exist. We'll see examples of that later. The coefficients e and the roots z, and I just write the e and z to represent all the coefficients, and z to represent any one of the roots, can be functions of other variables, which can also possess their own derivations, but we hide those variables and derivations for now. Okay, so we call the differential, right. So for non-negative k, with the kth iterative of the derivation, d is denoted with a superscript k in parentheses. We call the differential ring generated by the coefficients e of p and total derivative d, given by z braces e, the base differential ring of p, or the d ring of p. The d ring z z braces e is automatically closed under the partial derivatives of, I'm sorry, I keep under the partial derivatives with respect to the elementary symmetric functions. Okay. Sometimes we will need to deal with denominators and quotients instead of just differential rings. Let z be a formal variable. Then z braces e comma z is just the polynomial ring in z and derivatives of z over the base differential ring. And this denotes the d ring of formal derivatives of the e and z. Let q angle brackets e be the base differential field of p. We generally won't have to deal with this full differential field, but with a smaller differential subring of q parentheses e adjoin polynomials into derivatives of e, where denominators only involve 0th order derivatives of the e. Let z be any single root of p, then adjoining z and all its derivatives to this base differential ring is equal to the polynomial ring in z, because the derivatives of z are in because z is algebraic. The derivatives of z are all in the polynomial ring in z over q adjoin E and the derivatives of E. So in general, if we don't adjoin a root Z to something, we refer to the differential rings and fields generated by just the E as being base objects. So let R be any ring of characteristics 0 and M a positive integer. Although we'll only use it a few times, it's still useful to find R braces E subscript M to be the ordinary non-differential ring of derivatives E up through mth order. So the M plus first derivative is not in there, so that's not closed under that derivation. But so this is not a differential ring, but it's just useful to keep track of how many derivatives of E we're talking about. We define the weight of a monomial with a monomial product of EJ, the kth derivative of J to the UJK power, where UJK is a non-negative integer and only finitely many are non-zero, to be the weighted sum of those exponents, J times UJ, weighted by the weight of the elementary symmetric function, and we notate it with absolute value signs. And we define the differential weight of the same monomial, and again, you have to specify the derivation D, to be the weighted sum of those exponents, notated as absolute value sub D. So for okay, I got it. Okay, I just keep moving this. All right, so if F is a polynomial here in the E and the derivatives, here's an example where F has homogeneous weight 23 and homodifferential weight 8. If you counterexample, this polynomial E1 squared plus 2E2 prime, that has weight 2, but no well-defined differential weight. And then E1 triple prime plus E2 triple prime has differential weight 3, but no well-defined weight. So let K sub D denote a field of constants. Let's just say it contains the complex numbers. Field of constants with respect to derivation D. And let alpha be a constant with respect to D. Let Z braces E, square brackets alpha, denote the polynomial ring over the base differential Z braces E of the differential polynomial P. Constant alpha is assumed to have no weight and no differential weight. So we denote throughout y to be z to the alpha to be the solution of the logarithmic derivative of y divided by alpha equals the logarithmic derivative of z. And I just noticed my first error. There should not be an alpha on the right side of that. It should not be alpha over there. A linear ordinary differential resolvent, alpha resolvent, or a linear differential alpha resolvent, or simply an alpha resolvent of a differential univariate polynomial with distinguished derivation D is an equation over the polynomial ring in alpha and the base differential ring of finitely many iterates of the derivation D, such that R contains all linear combinations over constants K of the alpha powers of the roots, except that these alpha is not in these constants. So the CK don't contain alpha. Okay. So in other words, R is a linear ordinary differential equation satisfied by the alpha powers of each of the roots. Because R is linear, R itself does not depend on the field of constants. And a stricter definition of a resolvent is that its solutions are exactly all linear combinations of alpha powers of the roots of P and no more. However, we're not going to concern ourselves with that because may want to talk about differential consequences of resolvents being resolvents. So sometimes we'll use rather than defining a resolvent R as an equation, we define it as an operator, and we just write RY equals 0 to indicate that it's an operator on the power of alpha, power of Z. And we need to make one more generalization of a resolvent, and I did it. Okay, a linear partial differential alpha resolvent of a differential univariate polynomial with multiple derivations, and those multiple derivations can include just the partials with respect to the EK themselves, is a linear partial differential equation with finitely many terms over this base polynomial ring in alpha. It operates on a y that includes the alpha power of every root as a solution. Okay, so as I said, we need to include this more general definition when we get to the examples that involve the Python programs. So the weight of an ordinary differential alpha resolvent are given here, expressed as r sub im as a coefficient of alpha to the I and the mth derivative. The weight of it is the weight, as long as the RIM are all homogeneous, of the same weight and the same differential weight. Then the weight of an ordinary differential resolvent is the weight of any one of those coefficient functions. And the differential weight of R is the differential weight of any one of the coefficient functions, plus the differential weight of dmy, which is m itself. So that way, the entire differential resolvent R has a well-defined differential weight. And this is not to be confused with the differential order of Y, which is the derivative of highest order. Okay. The conian of P is the linear ordinary differential alpha resolvent among all possible resolvents where the R sub im collectively share no common factor over the base differential ring. So it's the resolvent of least weight. And I try to use theta im for R sub im of the conian. Okay, this is blocking my view. We refer to a power sum formula discovered in 1997 as a general class of methods of computing the unknown phi terms. So I'm just going to use phi to represent this number of R sub im. It's a general class of methods for computing this terms in a given ordinary or partial differential alpha resolvent. Here I rewrote the subscripts on R in a different way. The R's are in the base differential ring, and there are derivations again on the base differential ring adjoining polynomials in Z. And this general class of methods is replacing the indeterminate constant alpha with an integer, hereafter referred to as Q, and summing R over the n roots of P to obtain a system of linear equations in the derivatives of those power sums. And Q is one fewer than the number of undetermined coefficient functions. And then you solve for the R sub k by setting R sub k equal to the determinant of the phi minus 1 by phi minus 1 submatrix of this system of linear equations. And it is important to note that the resolvent R may be it's important to note that this resolvent R has to be polynomial in alpha for this power sum to work. So, history of differential resolvents. Robert Harley coined the term resolvent of a polynomial in 1862. Arthur Cayley computed the first resolvent of a polynomial, the trinomial, in 1862. Given here, I just mentioned resolvents of differential polynomials overlap with d-finite functions. Just so you kind of here's the set of d-finite functions. Here are functions algebraic over the e's, and they satisfy differential resolvents. And when those e's are algebraic themselves, of algebraic functions of x, then in that overlap are functions that are d-finite functions and satisfy differential resolvents. Okay. Giuseppe Bellardinelli computed the first alpha resolvent, so for arbitrary powers of trinomial in 1921 and 1922, and this is what it looks like. Counterexample: let P be a I'm sorry. It's important to note that one cannot simply write down a resolvent in any form and expect it to exist. So let's say P is a quadratic polynomial. Okay. Then there exists no partial differential alpha resolvent of the form R1 partial y with respect to E1 plus R2 alpha partial y with respect to E2 with R1, R2 in the base differential ring. If there were, then upon setting alpha equal to q equal to 1 and summing over the two roots, you would get this equation, and you'd get r1 times 1 plus r2 times 0, and we just force r1 and r2 to be identically 0. So from now on, we consider the roots of p to be differentially transcendental, at least up to nth order over the field of constants with respect to derivation d. In other words, the transcendence degree of this polynomial ring and the derivatives of e up through nth order over z equals n times n plus 1. So, right, e1 up to e sub n, and then up their nth derivatives. It's the total of n times n plus 1 variables. So far, we've implied that all alpha resolvents are homogeneous, not referring to as homogeneous in weight, but homogeneous as linear differential equations. You don't have something on the other side of the equal sign. That's because it's impossible for an inhomogeneous alpha resolvent to exist when alpha is not algebraic, and probably when alpha is not an integer. When it is an integer, then an inhomogeneous linear resolvent does exist for that particular integer q, but we're not going to concern ourselves with inhomogeneous resolvents. So, theorem, there exists a resolvent called the standard alpha resolvent of P of the following specific form. It has this phi sub n is this number of terms, n is cubic in n. I mean, phi is cubic in n. The powers of alpha go from 0 up to n choose 2 plus 1 minus m for the m equals 1 through n derivatives, and then except for m equals 0, where it starts at 1 and goes up to n choose 2 plus 1. It is important to note that phi n be 1 mod n, so that the resulting matrices in the power sum formula for the standard resolvent will be square, whose sizes are divisible by n when we get to factoring this thing. So this just follows. This is just basic linear algebra, vector space theory. Okay. So again, we're going to be talking about differentially transcendental coefficients of the polynomial. The proof that this power sum formula for the standard alpha resolvent is not identically 0 is extremely hard, but it's done. The power sum formula applied to the standard resolvent does not yield the conian of the standard resolvent. In fact, to this day, we still do not know what the conian of the standard resolvent equals, or even what its weight and differential weight are. Although we have an upper bound on the weight of the conian, I'll show that later. However, there is a known common divisor over the base differential ring of the 2n plus 2 outer terms, and that's the subject of this talk. I think I've made a breakthrough on figuring out how to pull out this common divisor from the other terms. And if I say outer terms, let me just go back up. You look here, for a given derivative, the outer terms would be r sub 0 comma m and r sub n choose 2 plus 1 minus m comma m. So it's the powers of lowest power in alpha and the highest powers in alpha. Okay.
John,
Yes.
sorry for interruption.
Sure.
The power sum formula, is the formula you just showed, is this the power sum formula, or you're just gonna get to that later?
Oh, the power sum formula. Well, that was shown. I'll just show that in an example. I mean, I just defined that power sum formula before the general class of methods. I'll show it for a quadratic. I'll demonstrate it for a quadratic.
Okay.
You'll see. Yeah. You'll see. So I have to first, even to define how to factor this. First partial. Okay, I'm looking at the time here. Okay. So I just need to use three sets of identities. First identity says that for any power of a root z, partial derivatives of powers of roots depend on only two parameters, length L and W, where in the partial derivative with respect to the E1 through En, the total differential order is the same, and this total weight, the weighted sum, is the same. And this does not, but this partial derivative has to be applied to z to the alpha, or powers of alpha. I mean powers of the root. does not work on arbitrary functions of E, and the terms length and weight come from McDonald, where the order of the derivative with respect to EK represents the multiplicity of the integer K in the partition of integer W and length L. So we call this partial LW the LW partial. We say it has length L and weight W, or actually order L. When applied to any homogeneous polynomial, LW partial reduces the weight of polynomial by W. So if F has a given is a homogeneous weight, LW partial on F has weight of F minus W. And just to show a counterexample here, if you apply, for example, the simplest or the smallest non-trivial case is the partial with respect to E1, partial with respect to E3, and the second partial with respect to E2. You apply the partial with respect to E1 and E3 to E2 cubed, you get 0. But if you apply the second partial with respect to E2 to E2 cubed, you get 6E2. So those are not equal, but okay. But for a polynomial, here's for take a polynomial of any degree, the fourth power sum of the roots, those partial derivatives are equal. Del 2, 4 equals del 1, 3 on P4. Okay. So important fact, you can actually sum the lengths of del LW on L prime W prime equals del L plus L prime W plus W prime. Again, operates on powers or power sums of the roots. Expansion of derivation, total derivation in terms of those partials is given by this. On the general differential ring, you have technically infinitely many derivations, derivatives, but on just the nth, derivatives up through nth degree, it looks like this. And so the point is that the derivation can be expressed as linear combination over the base differential ring of base differential ring of partials LW. By the way, I'm sorry, you see my mouse, right? Okay, the cursor, I mean, right?
Yes, we can see you.
Okay, I just want to make sure. Okay, so the cubic n, so let's just take for the cubic n equal 3, the total derivative is this sum of, here's the expansion in terms of partial derivatives. And then second derivative, notice it has to be, it requires partials 1, 1, 1, 2, 1, 3 up to del 2, 6. Okay, second identity we need is that we treat now Q as an operator on P sub Q. Q times PQ is the weighted sum of the partials. So it's I times EI partial with respect to EI of PQ. This is given in Sturmfels. It's probably due to Euler. Or you can just look up the Gerard-Waring formula for power sums, and you can just differentiate it and verify the identity directly. And so here, sorry, right. So here's Q for the cubic, and then here's Q squared, and notice it expresses a sum of del 1, 1 up to del 1, 3, and then del 2, 2 up to del 2, 6. An important notice that the weight of each coefficient of each partial derivative operator matches the weight of the operator. So in other words, for example, here, 2 squared E2 squared 1 times E1, E1 times E3 times del 2, 4. This coefficient has length 2 and weight 4, which matches the LW on the partial LW. All right. So in the third partial identities, I don't really know. I proved them in my dissertation for myself. They may be out there elsewhere. And basically, it expands the partial derivatives of, well, 1 comma W in terms of higher order partials, the LW partials, except when L is greater than or equal to 2, then you've got denominators. So it's an expansion over rationals, not integers. And the entire point of this identity is it allows you to express LW partial as a linear combination of partials of distinct weight, W through W plus W minus L times N. So all of the same differential order W. So cubic, here it is. Here's del 1, 2, del 1, 3 expanded in terms of the order 2 partials. And so if we combine the previous identities, here's what Q is for a cubic expanded. Notice it's expanded in terms of LW partials of weights 1, 2, 3, 4, 5, 6 uniquely. There's no partials, two partials of the same weight. And here's the total derivation operator. Again, del 1, 1, 2, 2, 2, 3 up to 2, 6. And notice the differential weight of the monomial minus the differential weight of the LW partial is, again, constant at 0. To expand, so let's say here I show expanding DQ as a linear combination of partials. I'm going to just write it down. This is what it is. Okay, so we define this square brackets del LW subscript DMQI to be the coefficient of the partial derivative in the operator DMQI after all three identities have been applied. This, I'm actually hiding the basis that you're showing here, because the third identity you can you can repeat arbitrarily. You can to higher and higher orders. So definition, we call the matrix containing these coefficients, these coefficients of these partials for these operators, a transition matrix for any LW pairs, LW, and any set O of operators DMQI. We call the square brackets DMQI with IM in some set O and Q is some set of positive integers. Call that the operator power sum matrix. And finally, we call the partials, we're going to need this with the square brackets, LW partial on PQ. Again, LW is in some set and Q is in some set of integers. This is the LW power sum matrix for any set of pairs. Example, and just want to show an idea what we're going to do. So here's a 3x4 matrix of operator power sum matrices, 3x4, and it's expressed as a product of a 3x6 by 6x4. So here are the operator coefficients, and then here are the LW power sums. This is a 6x4, and okay, the 6x4 matrix though happens to have the last two rows are all 0. So in fact, this 3x4 matrix factors as a product of even smaller matrices. It factors as a 3x4 times a 4x4. So that's just to give an example of what we're going to be doing. So the main factorization of the power sum formula is, well, it has been a conjecture. I think now it's going to be proved that this particular transition matrix of coefficients of these LW power sums with respect to these DMQI operators, that this factors out of all phi terms of the standard resolvent. And we call this the standard transition matrix, where LW goes from 1, 1, 2, 2 up to n choose 2, comma n choose 2, and then the order stays put at n choose 2, but the weight goes up to n times n choose 2. We know for certain this conjecture is a theorem for the outer terms of the standard resolvents. Yeah, right. So these terms I've known since 1999, but only since December do I now believe I found a way how you factor it out for the other terms. And just why are we talking about factoring? Okay, so the weight of the unfactored power sum formula for the standard resolvent is of order n to the 6. This is what it is. And after factorization, it's of order n to the 4. And the differential weight of the unfactored power sum formula is quartic in n, but after factorization by this theorem, it drops down to quadratic in n. And another theorem that I've known since, again, 2000 is there's this upper bound on the conian for the standard, for the weight of the conian for a standard resolvent. And here I do for the quadratic up to a quintic. Here's the number of terms, 5, 13, 29, 56 is the number of terms. And here's the weights before you factor, and here's the weights after you factor. Here's the conian. Here's an upper bound on the conian. For the quartic and higher, the weight of the factored resolvent exceeds the upper bound on the weight of the conian. It's implied in the main factorization theorem still does not bring us down to the conian, so more factoring needs to be done. Oh, okay, so here's the quadratic. Here's the standard resolvent for a quadratic. It's got 5 terms. Again, I try to use U for unfactored. And so you plug in 1, 2, 3, 4 for alpha, sum over the 2 roots, you get a system of, it's basically a 4x5 matrix in the U, and you solve for the UIM by setting UIM equal to the relevant matrix minor. And so this is what, here's U sub 0, 2 equals, and here's how it factors. It actually happens to have 2 factors of this E1 prime 2E2 times E minus E1 E2 prime times this matrix of these power sums. Okay, here's U sum 0, 1. Here's how it factors. I think I might have right. So and then here's how U1 1 factors, and here U1 0 factors, and finally U2 0 factors in this way. And so what remains after you pull out this factor is here's the leading term, which happens to have a does have one extra power, one extra factor itself of this matrix, determinant of this matrix. But here's what the remaining terms. So it's a mixed operator power sum, LW power sum matrix. Okay, so this unfactored resolvent is differential order 4 and weight 10, and has differential weight. I should have said differential weight 4. Differential weight 4 and differential. The factored resolvent has differential weight 3 and weight 7, and it can't be factored further. So this is the conian of the quadratic. So, okay, we can just here we go. So why talk now? It's what I figured out in 2022. For the cubic, here we have 13 terms in the third order resolvent, in the standard resolvent of the cubic. Unlike with the quadratic, we now have middle terms. That means powers of alpha on the derivatives, dmy, in between 0 and the maximal power of alpha for that derivative, which is n choose 2 plus 1 minus m, which is, in this case, 4 minus m. Except when m equals 0, then the powers lie strictly between 1 and n choose 2. So here, that's the middle term. These are the middle terms, and those are the middle terms. So we define O sub O parentheses 3 to be this collection of to be the set of pairs that satisfy the main factorization theorem that I showed earlier. I plus m goes from 1 up through n choose 2, which is 3. These pairs represent dmq to the I applied to qy in the bottom 9 rows of U0, 3, 0, 2, 0, 1, and 1, 0. And they represent dmqi applied to y in the bottom 9 rows of U13, U22, U31, U40. So again, the power sum formula is going to lead to it. You're going to have the 12 by 12 matrix, and you're going to have to you have to break that matrix into parts, the top 3 rows and the bottom 9 rows. So LW3 parentheses 3, which is 1, 1, 2, 2 up to 3, 3, and then 3, 4 up to 3, 9. This is the set of pairs satisfying the main factorization theorem, where L goes up to n choose 2, comma n choose 2, and then the weight goes up to n times n choose 2. So this represents the partial, again, the partial derivatives. And then I have to introduce this set of lopped off operators. I'm sorry, lopped off, not power sums. Sorry, lopped off LW partials. So this is what you take. If you take LW4, where the order goes up to 4, and then the weight goes up to 12, and you lop off the weights greater than 9. So you lop off 10, 11, and 12 here. Okay, so just to show what the one of the terms, the outer term, we already know how to factor. It factors as this this 12 by 12 times this 12 by 12, where here's the coefficients of the LWs with respect to DMQI, where IM runs through order operators with I plus M less than or equal to 3, and the LW partials are in this set LW 3, and here's what remains in the resolvent. So this is the lower 9 by 12 matrices, and these are the top 3 rows. Okay, and right. So the 12 by okay. So and here's for U13. Here's how it again, this factorization. The same factor pulls out. But let me get to okay. All right, we factor this determinant of this transition matrix out from the leading terms in the same for U22, U31, U40 in the same way we factored U13, because U22, U31, those are the highest power on alpha in those derivatives. And we factor out the same determinant from U03, U01, and U10 in the same way we factored out U02. Those are the lowest powers of alpha in those derivatives. But when we get to the 5 middle terms, we have a problem. Yeah, I see I've exceeded my time, but am I allowed 10 more minutes, or is that too much to ask for?
Yeah.
I mean, I'll try to go fast. I mean,
if you can wrap it up. So maybe you don't need to go through all the details, but if you can give an overview.
Okay, I do want to get to the Python because yes,
focus on what is more important for you.
Well, this is actually, I mean, this main theory, this and the Python programs. So here we basically the method for when you get to U12, what happens is you can't factor out a 9 by 9 matrix. You can factor an 8 by 9 by 9 by 12 transition matrix. And the problem is because here I will there exists no 9 subset of these 12 operators that appear in this the power sum formula for U12, such that either I plus M is less than or equal to 3, or that this 9 subset equals DMQI applied to Q. In other words, like it's shifted by Q with I plus M is less than or equal to 3. So that's the problem. There's no 9 subset of these 12 operators where I plus M is less than or equal to 3, or it's the shift of by Q of a set of 9 operators. And so I finally figured this out in December. You have to add linear combinations of the first 2 through 6 columns to the to row number 10, to column number 10, to column number 11, to column number 12. So for the first 9 columns, Q between 1 and 9, cannot expand those derivations in terms of partial derivatives of order less. Right. So you get to the problem with you have D square, Q square, PQ row. That's the problem. We require partial derivatives of order 4 also. So the first 9 columns we can factor, but you actually have to express it in terms of partials of up through order 4 over this lopped off set of partials. When you get to the 10th column, you first expand d square q square pq as in terms of second order partial on q square pq. So here's del 1 up to del 2 on q square pq. You add linear combinations of the columns to eliminate those del 2 through del 2 terms. Again, adding linear combinations does not change the determinant. And you end up with a system of 5 unknowns, and you solve for them. It's a triangular matrix for these unknowns. And because the partial derivatives of weight W, where Q is less than W, are 0, its determinant equals an integer, meaning you've got no monomials in the denominator. And the column, so here's the 10th column, gets replaced with this linear combination, this modified one. You do the same for the columns 11 and 12. This is what remains in, here's the column 10. Here's column 10, row d square q square. And you do the same thing for columns 11 and 12, but with a different set of linear combinations. A different set of coefficients that you have to solve for. And then there's one more modification to expand these. We've expanded these modified columns in terms of basis 1, 1 up to 3, 9. But the 9 by 9 transition matrix T99 that I showed earlier is actually in terms of this lopped off LW4, goes up to a 4, 4, 4, 9. So you gotta do something. This is not the same basis. So you actually have to just add linear combinations of columns 7, 8, 9. You eliminate the LWs of weight 7, 8, 9, and you can then expand. Okay, the remaining LWs are in this smaller subset. Then you put these, when you put all these pieces together, this is what this term F12 factored looks like. And this is what this is the lower 9 by 3 entries of that matrix. And so they've all been shifted by these coefficients. And for these 3 rows, the 1, 3, 3, 1, 4, 0 rows looks like this. Okay, so now the application of resolvents. Well, I figured do something. I try. You can try to prove Fodde-Bruno's formula for the nth derivative of a composition of functions, and trivial for a case equal n. But you can actually use this resolvent to do it for n equal 2 and 2 intermediate variables. And here I'm actually showing how you determine which resolvents exist. You take the okay, so here's, I said del y over alpha y equals del z over z. Then this is where del represents any partial, any derivation. So del z equals a plus bz, where a, b are in the base differential ring, actually with the denominator in the discriminant. So here I just start using stars to indicate general elements. They're not, this star does not equal that star. They're different. So del y is in the base polynomial ring in alpha. And then when you apply a second derivative to that, or derivation to that, it could be different or the same. You get del prime del y equals alpha y times a sum of 1 z alpha and alpha z. So you got 4 terms involving z and alpha, where the star again are in this base differential ring. They don't involve alpha or z. They don't involve, and that's the entire point. So if you go through this, you go, let's say alpha prime alpha equals the total derivative. Here's d squared y over alpha y is the basically a dimension 4. Del when del is del 1 1. Again, here it is expanded. Just happen to have 0 for these two terms. When del prime equals del is del 1 1, you get here's del 2 2y over alpha y. Again, is here's it's a vector space over z and alpha. You so set up the equations. You get a 5 by 5 equations in these logarithmic like derivatives, and so you set the determinant to 0, and you have a resolvent like this. It looks like this: total derivation d, partial derivatives 1 1 2 2 2 3 2 4. So after you clear denominators, so 5 unknowns means the power sum requires 4 power sums, and finally you're computing 5 by 5 determinants of 4 by 4 matrices. And now here we have a Python program to help factor out, to actually compute the power sum formula. And this is what you get. So let me just show you this, and because we worked hard. And I'd like to thank my brother Paul Nahay here, who's helped a lot with the programming. Here is what the, oh, wait a minute, I have to share that. Hold on a second. New share. Spider. There you go. You see the Python program now?
Yeah, we see it.
Right. So this is what the code looks like for the power sum for the 5-term, right? And if I run it, right? Well, okay, should be fast. Okay, well, there it goes. Actually, this is at the bottom is the resolvent after you've pulled out factors. I do have to. Okay. Okay. Have you stopped seeing the PDF? Then I have to go back to the.
Yeah,
PDF.
the PDF is gone.
Right, the PDF is gone, so I have to go back to the Right. So you have to just apply one more identity, and you get this. This is basically a resolvent. But the neat thing about this is, even though it's came from a quadratic, it's actually true for any functions y of e1 and e2 of x. Just although full disclosure, the computation of the second derivative of PQ involves a Fodor-Bruno formula, but it's a neat proof of concept of using this. And it's important to set up the correct resolvent. If you set up a different one here with this set of partial derivatives and total derivation in 6 unknowns, you will get returns all identically 0 values. So I go back to I go back to the if I do it that set of, if I do it that resolvent, it gives you get number of non-zero factors is 0. So wait a minute, here we go. Okay, I'm putting in the wrong. Right. So if you set up this 7-term resolvent, and do the same thing, you get it returns 0 for this this term here, but non-zero for the other f's, but it's not the Fodor-Bruno formula. And if you set up a 9-term resolvent of this form, it returns identically. The power sum formula returns identically 0. So that's, I'm not covering this. I didn't want to cover this. Dr. P. Mantle helped me with trying to count the actual monomials in a resolvent. But thank you. That's I want to thank my brother Paul Nahay for helping with the Python program, huge help, and Dr. Robin P. Mantle at the University of Pennsylvania for trying to help me count monomials. All right, thank you very much.
All right, thank you, John.
Okay, stop sharing. All right.
Are there any questions or comments? Just feel free to unmute yourself, or you can also ask in the chat.
Right. Right. All right. So.
Okay. I think your talk is quite impressive in its technicalities and calculations. And of course, you also have some theorems. But after listening to you, I did not get a view of what are the methodology that you're using other than most likely linear algebra. So could you give an overview of the ideas behind the calculations?
Well, I mean, basically, I said this power sum formula is a kind of a general class of methods for computing these resolvents. I mean, that's sort of the general class. And I've kind of figured out different ways it generalizes. I mean, I figured out even, I mean, I don't want to get into more generalizations of the resolvents, but yeah, I mean, it is surprising. I'm just surprised at how deep I go with just linear algebra in finding these patterns. I mean, I guess.
But excuse me, but but it seems that you're doing very special examples, applying these calculations. I mean, you look at certain columns and you do some certain linear combinations. So is there some more abstract kind of ideas, theoretical things than brute force calculations and ingenuity in observing patterns?
Well, I mean, I wish there were, because I mean, I've been just that. I mean, just computing how this one term of this one cubic resolvent factors. I mean, I worked on that for 23 years trying to figure out how to do this for, you know, I mean, I know in my head how this generalizes to alpha resolvents of any, the standard resolvent of any order. And in fact, the derivatives don't even have to be consecutive derivatives. I mean, in fact, so I envision in my head, but actually, in a way, the factorization is still, it's not really making use of any deep abstract ideas. I mean, I wish it would, and maybe there is some way, but I just struggled 23 years trying to figure out how to even factor those middle terms, and you know, and I think there's probably even a way that you can repeat, you know, factor further, using the same ideas. But yeah, I just kind of wore myself out just trying to get this. And as far as the more abstract things, that's why when I went to counting like the number of monomials, I had this Dr. Robin P. Mantle, who's the author of this book, Analytic Combinatorics in Algebraic, in several variables. He spent 3 hours with me talking about his work and trying to, you know, estimate, you know, give an asymptotic bound on the number of monomials of a given weight and a different differential weight. And yeah, so that's actually, I didn't show that. That was at the very end, but that involves Cauchy integrals, multivariable Cauchy integrals, and then it has to be over. So you know, that part of it is uses abstract, you know, math. You know, I mean, in fact, I still don't understand how to do that, and Dr. P. Mantle himself has said it's actually pretty hard to do, to get an acid. It's like Hardy's formula for the asymptotic number of partitions, but you know, with further for partitions of an integer, but with further conditions. So I wish I could give you a better answer about finding, you know, using more abstract methods, and maybe one will come along once I really work out, you know, how to do this factorization in general. But I just first wanted to prove that it could be done. Okay, so
for example, you have this LW4, the lobe all.
Right.
How does that come about? I mean, how do you think about that, even just for any particular calculation? I mean, why 4, not 3 or anything else?
Well, because you're expanding these partial, it comes out because the main factorization theorem says that you have to expand the the partial derivatives as okay. Remember when I said that okay, I used the letter phi of n
Yeah,
to represent the number of terms r sub im in the resolvent.
Right.
When r sub im is the power, is the coefficient of alpha to the I dmy. R sub im is a huge polynomial in, monomials in these. So, and I said that the phi is one mod n. So the factorization is leaving n rows unfactored. So like this is a 12 by 12 matrix, 3 divides 12. And the top 3 rows, the reason it's 3 is for a reason, because n equals 3, n is the cubic, and the factorization is basically factoring out everything except the top n rows. So that's where that comes about. N choose, well, the 4 is n choose 2 plus 1. So 3 choose 2 plus 1 is 3 plus 1 or 4. And that's where the 4 comes about. It comes from the factorization theorem. Okay. I didn't want to, it was hard enough to show this one very specific example. I was not going to try to do the general, you saw how hard it is to do the specific case, and to try to do the general case, it would just,
okay,
be completely ununderstandable. So thanks for your question. Yeah.
I have another question if nobody asks, but I will let somebody else have a chance to ask first. No?
That's okay.
Now, you start with a polynomial p with
Right.
the coefficient being the symmetric functions of the roots.
Right.
So are you assuming that the roots are distinct then?
Well, for the moment, yes. In fact, I have to get into all the combinations of different conditions on the roots. That's why I just said, let's just consider everything being differentially, the roots being not only transcendental, but differentially transcendental up through nth order. So that means all polynomials, right? So
I see, okay.
up through nth degree, it means the coefficients are differentially transcendental over the rationals. So yeah. Especially then, what happens is probably in with the Python programs, you get 0 because there are relations. What's going to happen is you will get this thing that factors this main factorization, this transition matrix that factors out. Its determinant is 0 for those particular resolvents that I showed there with the Python program, because that determinant of that transition matrix is 0. Let me just go back. What do I have highlighted here? I'm sorry. I have. Okay, share screen. Let me just see. Okay, I have the PDF. Let me go back to the. Right. So this is. Okay. We can go here to, here's an 8, but here's the 8 by 9. This actually takes a while. Well, this actually takes about 3 minutes to compute. So I'll just have that on in the background. But yeah, I just think where am I? I'm looking for. Okay, I can't. Sorry, I'm trying to see. I can't. Uh-oh. I can't see you guys again. I'm sorry. Hold on. I think there we go. Okay. You guys vanished for a second. Yeah, so
John, I'm sorry, I'm interrupting. I'll have to go. So I'm gonna stop the recording just now, but then you can continue.
Okay, that's fine. Thanks a lot. Okay.